Tonight's speaker is the recently appointed director of the NNCO, which is the National Nanotechnology Coordination Office. Got that right. But previously, he's been seconded from NASA, where he was managing the nanotechnology project in the Game-Changing Technology Program, which involved 5 NASA centers, industry, and universities working together to mature nanotechnologies with high potential for impact on NASA missions. God, I can't say that. Amongst his many accolades, he's been recognized as the NASA Glenn Small Disadvantaged Business Program Technical Advocate of the Year and the NASA Small Business Program Technical Personnel of the Year. He also received the NASA Equal Opportunity Employment Medal for his work to increase the involvement of faculty and students from minorities. So yeah, without further ado, I don't think there is anyone more qualified to be giving you an introduction to nanotechnology. It's my absolute pleasure to welcome to the stage. And just before I do, I have to give a big thanks to Loxon, and particularly to Harry Bashong and to Alan Gelwick, who are both of whom made this event possible. So very, very big thank you to you for organising this trip to the UK of tonight's speaker. So sorry, just thought I'd get that in. But yes, please give a big welcome to your speaker tonight. It's Dr. Mike Meador. Thank you very much.
Well, thanks. It's a pleasure to be here. I'm really honored and thrilled to be in this esteemed location here to talk in a place that Professor Faraday not only did his research, but talked about the results of his research. And I'm really excited to talk to you and tell you about nanotechnology, but I want to do a couple of show of hand things. First of all, how many of you know what nanotechnology is? Okay, how many of you are practitioners of nanotechnology? Okay. And I'm going to steal this from Terry, who mentioned this earlier today, but how many of you know that you brought some nanotechnology with you here tonight? Okay, so the other thing I want to tell you is I don't think I've ever spoken to a group, an audience this large, and I'm trying to contain myself from not taking a selfie of this moment, but I'm really excited. Yeah, so but I can't take selfies. I'm terrible at it, so it would be really bad. So I'm gonna stand away from the screen here a bit. I'm really excited to tell you about nanotechnology, what it is, to point out to you that nanotechnology is around you. If you have one of these cell phones, these smartphones, you have nanotechnology in your pocket. And we'll talk about some other examples of where nanotechnology really is in commercial products that are available today. I'm going to also tell you a little bit about what the United States has done in nanotechnology, in particular the U.S. National Nanotechnology Initiative. So some of that's going to be a little bit drier than maybe perhaps some of the cooler aspects of nanotechnology. So we're going to talk about just what is the nanoscale, what's unique about nanotechnology, some examples of nanotechnology-based products that are currently available, a little bit about where I see nanotechnology headed in the future, and then we'll do a wrap-up on this. So what is nanotechnology? And this is off of our website, the U.S. National Nanotechnology Initiative's website, Nano.gov. And if you look at the pictures on the left, you can see sort of a perspective in terms of scale. So a carbon nanotube, the diameter of a single-walled carbon nanotube, is roughly 100,000 times smaller than the diameter of a human hair. And that diameter of the human hair is about 100,000 times smaller than that of a modest house. So you're talking about something that's quite small. And what happens, the sort of official definition of nanotechnology for the NNI is that it's typically dealing with control of matter at a scale of about 100 nanometers or less. And the reason for the 100 nanometers is that once you get to that length scale, that small of a length, then conventional physics starts to break down and some really neat things start to happen. Now, there's a lot of debate about, is it 100 nanometers, is it 300 nanometers, and really the whole point here is that once you get small enough, things start to happen, and those things can be exploited to make new materials and new devices that really have the potential to do some pretty amazing things. So within the US, actually a little more than 15 years ago, January 20th of this year, President Bill Clinton was convinced that nanotechnology really had the potential to have a huge impact on the economy and world economy and on society in general. And so this vision has been articulated. So we formed the National Nanotechnology Initiative with the idea that really the ability to understand and control matter at the nanoscale will allow you to do revolutionary new things. You know, I used to be involved in this program at NASA called the Game Changing Technologies Development Program. I don't know if game changing is used much here in the United Kingdom, but in the United States it was used a lot when we developed the Game Changing Technology Development Program, so we used to get snickers about it. But really, you know, a game changer is something that really sets a whole new paradigm in how we would do things. And that was the vision here with the NNI. And I'm here to tell you that it's a reality. So everything that you see up there, with the exception of that car in the bottom right, is actually a product that's been developed and most of which is commercialized, but we'll talk about that a little bit later. So the National Nanotechnology Initiative is a coordinated initiative within the US federal government amongst all of those agencies. There are about 20 agencies involved. And about half of them have funding, actual funded programs in nanotechnology research and development. And the others are like the Department of State, Department of Education, that have an interest in nanotechnology and are actively involved in certain aspects of it, but they really don't have funded programs. The goals of the NNI are, first of all, to advance world-class nanotechnology research, to foster the transition of nanotechnology discoveries from the laboratory to market, to develop the infrastructure, both in terms of world-class facilities to see things at the nanoscale and to fabricate things at the nanoscale. And these facilities are facilities that are fairly large and expensive, so that one single institution would not be able to fund those on their own, but government could do that. And then also at the same time to develop the skilled workforce to allow us to do work in nanotechnology, whether it's the individual working in a factory that's making a nanomaterial or a nano-enabled product, or whether it's the scientist in the laboratory that's you know, doing new discoveries that we will later commercialize. And then the last goal is to support the responsible development of nanotechnology. What this means is we want to be responsible in terms of making sure, as much as we can, that the products that we develop are safe for the public, for consumers, and for the environment, both today and in the future. And then the second thing that we want to do is we want to tell people about the benefits and risks of nanotechnology. We want to be transparent about this and say, okay, you know, nanotechnology will do this for you, and oh, by the way, we know that these are the limitations in terms of what it can't do, and these are the risks that you need to understand, so that people can really be informed about this important technology. So right now, the United States government, as of the US President's request in 2016, has spent about $22 billion in nanotechnology R&D since its inception in 2000. And actually, this chart starts in 2001, because in 2000, what happened was we were past the initiation of the budget cycle. And so what happened was that some agencies said, okay, we have stuff in nanotechnology, and we're just going to coordinate it. But real funding started to happen in 2001. It's leveled off at about $1.5 billion US per year, and it's been fairly consistent. The way the NNI is operated is that those 10 or 11 agencies that bring in the $1.5 million a year have their own mission goals and needs and objectives, and so they fund work in nanotechnology because they feel that nanotechnology is a way of helping them to achieve those goals. And so it's incumbent on my office, the National Nanotechnology Coordination Office, to make sure that we find opportunities for these agencies to work together so that we can push these 4 goals of the NNI that I talked about on the previous slide and make them a reality. I mentioned responsible development of nanotechnology, and we feel that this is an important thing to do. It's an important area to invest in. Actually, some of the very groundbreaking work in EHS was done in the UK with a report by the Royal Society in 2004, and it actually spurred a more focused look at EHS in the United States. But right now we're spending about 10% of the NNI budget, and over the lifetime of the NNI, we've spent about $1 billion in nanotechnology R&D. And So some other Nano-Factoids. Worldwide governments, corporations, and venture capitalists in 2012 invested just under $19 billion in nanotechnology R&D. That's an 8% increase over 2010. Of that $18.5 billion, the US contributed about 30%, 36% of that amount. And in terms of government and corporate spending, we lead the rest of the world in that area. Corporations expanded their spending by about 21%, governments by about 5%, and private investors by about 10%. That's 2012 versus 2010. For what's the impact of all of this? The global value of nano-enabled products and intermediates and nanomaterials is predicted to reach something on the order of about $4 trillion by 2018. This is all work that came out of a survey that was done by the Lux Research Corporation in 2014. So a significant opportunity to really be disruptive technology and make a large impact on the world's economy. So in 2000, President Clinton gave a speech on January 21st of 2000. President Clinton visited Caltech and gave this landmark speech, and he really did a great job of articulating what nanotechnology ought to do, to the point where you didn't have to be a scientist or an engineer to appreciate the potential benefits. And he issued 3 challenges. He said, first of all, just imagine materials with 10 times the strength of steel and only a fraction of the weight, shrinking all of the information of the Library of Congress into a device the size of a sugar cube, and detecting cancerous tumor cells that are only a few cells in size. So 15 years later, what have you done for me, right? And so we'll talk about that. So the first is a little bit about high-strength materials. A classic example of this is graphene, and this is actually work that was done here in the UK at the University of Manchester. Andrei Geim and Kostya Novoselov received the Nobel Prize for this work in 2010. But graphene is an amazing material, extremely lightweight. You could make a single molecular layer of graphene that would be the size of a football field, and that would weigh less than 1 gram. Extremely lightweight material, extremely strong, over 300 times the strength of steel. And some interesting other properties. It's a ballistic electrical conductor. What that means is that it has no electrical resistance. So if I inject an electron, see if this works, over here, well, maybe not. Oh yeah. If I inject an electron over here, it will shoot through the length of the graphene at the speed of light. Okay, and if you think about that, if you think about making, for instance, power cables out of a ballistic conductor, think about the amount of energy that you could save by reducing the transmission losses that you typically see in cables. In fact, it turns out that some estimates from Rice University are that if you were to make power cables for electrical distribution out of single-walled carbon nanotubes, which are ballistic conductors, so a continuous single-walled carbon nanotube material, you would reduce the amount of transmission losses in the United States by the equivalent of 6 Hoover dams per year. So significant, I mean, really talk about energy savings, that's pretty amazing. Plus the stuff is so strong so this is one example, but I'm going to talk about another class of nanomaterial, and actually something that's getting very close to commercialization in terms of making high-strength materials that you might see in the not-too-distant future. So this is carbon nanotubes, and basically the story is the same in terms of the properties. Single-walled carbon nanotubes have measured properties about 150 times the strength of conventional carbon fiber, like those that are used in aircraft today, the Boeing 787 and the Airbus aircraft. That's 100 times better than aluminum. So the specific strength is the strength divided by the density of the material. Again, very tough material, so typically what you see is something that's quite strong is often not tough, that it's brittle and you can break it very easily. And then very high electrical and thermal conductivities. I happen to have the privilege of meeting and talking to the late Nobel laureate Rick Smalley, and Smalley got his Nobel Prize for developing or discovering, along with Fujiyama, buckyballs, and not Harry Kroto, I'm sorry, and buckyballs. And Rick did a lot of work, was one of the early pioneers in carbon nanotube-based materials. And he used to show this picture, not this one, but another picture of a cover from the American Scientist magazine of a space elevator. And the idea behind the space elevator is that you have this long tether very strong, and you have an elevator that rides up and down on this. And the tether is anchored somewhere on a satellite or a moving platform, or a platform in space. And this would be a way of taking people and supplies up and down, ferrying them up. And in order to be able to do that, you would have to have something that would have amazing strength. So Rick Smalley showed this picture for a number of years, and then he stopped showing it because he realized that it's a great vision, but what you would need to do is to make a single-walled nanotube fiber that was infinitely long. And the prospect of being able to grow that in his lifetime was pretty slim. And in fact, right now, the longest nanotubes that people have grown are something on the order of 0.5 meter in length. But time moves on, and we'll get there someday, perhaps. But we are getting close to reality here in terms of being able to use these materials and applications. So this is an example of yarns that are being made by a company called Nanotechnologies in the United States in New Hampshire. And this is a real-time picture of this. So what you're seeing on the left is a picture of a furnace in which these nanotubes are being produced. And this is in real time. They're really cranking out a lot of nanotubes, and then they can take these nanotubes and grab them and spin them into a yarn. And what NASA is doing, actually this was the project that I managed, was taking these yarns and improving the mechanical properties such that if you could make a composite that was twice as strong as the composites that are used in the Boeing 787 using this fiber, and they weighed no more than that composite, conventional carbon fiber composite, that you could reduce the weight of a launch vehicle by 30% by using that. There is no way that you can make that much of a weight reduction any other way. It is a true game changer. And so what we're doing, what NASA is doing, is actually developing the materials by working with companies like Nanocomp to get the strength of the material up, developing ways to make composites out of those materials, and then demonstrating them in a component. The component that they've chosen is shown on the left here. It's called a composite overwrap pressure vessel, and it's basically a gas bottle. And the gas bottle is used to hold a propellant. And in this case, what we're actually going to do is demonstrate this through a flight experiment. And the flight experiment will be on this sounding rocket here, and is scheduled to happen in September of 2016. And the idea is to take this composite overwrap pressure vessel, use it in place of one of these blue tanks here in a cold gas thruster system, and put it in an experimental payload on this guy. And we're going to do two things. We're going to wiggle the payload back and forth and use the sensors on board to measure that movement. And then the other thing is we're going to spin it up prior to its descent. And that's always done to improve the aerodynamics. So this will actually be the first example of a component made, a structural component made out of these composites. And it'll do a lot to taking nanotechnology to based fibers into a reality for aerospace applications. So stay tuned. Hopefully the launch will work, and you'll hear more about it. This is something that's actually has happened. So I mentioned the great electrical properties that carbon nanotubes have. And this is, if you could take, for instance, a conventional coaxial cable, such as what's shown here in the upper part of the screen, and you were to replace the copper core as well as the aluminum RF cladding, the radio frequency cladding that's an intermediate layer, with carbon nanotube yarns and with sheets, you can reduce the mass of that cable by somewhere between 30 and 70%. Depends upon the cable design. Here's a couple of examples of actual cables that have been produced that way. And why is that important? Well, the Boeing 787, and I apologize, I was going to convert this to kilograms, but the Boeing 787, and I didn't do it, the Boeing 787 has 8,000 pounds of copper wire in it. The space shuttle had 230 miles of wire in it. And about 60% or more of that wiring is in avionics, just transmitting data signals. So in the 787, it's for the TV screen and the controls in the airplane. So that's a significant weight reduction. And there's work going on now to take this even one step further, and that is enhance the electrical properties of the carbon nanotube material so you can start to think about doing the power cables, and you'll take more mass out of the airplane or the spacecraft and maybe even think about doing power transmission lines on Earth. All right, so enough of high-strength materials. What about the second one, shrinking all of the information at the Library of Congress into the device the size of a sugar cube? Well, so that was 15 years ago. The goalpost is moved, right? Because there's more stuff in the Library of Congress. I think it's 15 terabytes right now of information. But, oh, I'm sorry, I messed up. We're gonna skip ahead. I'll get back to the second goal. We'll talk about detecting cancer, rather. There's been a lot of work in nanoparticle-based diagnostics for detection of cancer and other diseases, and I'll talk about some other examples. But here's one that's actually pretty neat. This is a gold nanoparticles in which they have coated the nanoparticles with chemical groups, and at the end of the chemical group, they've attached a dye that fluoresces. And as long as the dye is bound to the nanoparticle, it does not fluoresce. But what happens is if you show this nanoparticle now to a typical RNA that you want to detect, the RNA will bind to the gold nanoparticle and it will eject that, that group that contains the fluorescent dye, and now the dye is no longer bound and it fluoresces. And so it's basically, they call it a nano flare, it lights up. And by doing this, it's possible to detect on the order of about 100 cells in a flow cytosis experiment. So you actually can probably detect a lot less if you didn't have this thing flowing. But there's a lot more examples like this. About data storage, another example of that is shown here. This is work in terms of using DNA, which is a nanostructure, and changing some of the amino acids in the sequence within the DNA to encode information. And when you do that, you can get to very high data storage rate, data information density, excuse me. So this chart here on the right shows a comparison of conventional data storage, you know, the CD, the DVD, Blu-rays, flash memory, the best hard disks. And this is the example of this work. So you're going from basically, and this is a log scale here, so you're going from, you know, 10 to the 10th to 10 to the 16th bits of information, and that's well better than or sufficient to store all the information that's on the Library of Congress. So just a couple of examples of how, you know, setting forth this vision and actually doing some work, we've achieved some significant goals. But what else about nanotechnology? Well, actually, it's nothing new. I was taken downstairs to see the gold colloids that Professor Faraday developed way back a few hundred years ago, and you know, that's an early example, but there's even earlier examples. So this is the use of gold nanoparticles in glass to make this Lycurgus cup, which is actually shown in the British Museum, and I took my wife Marianne on a forced march around the British Museum on Friday. Where's that cup? So this is my cup. I didn't do a selfie by the cup either because I'm terrible at selfies. But what happens here is that depending upon the angle at which the light strikes the cup, it can either be opaque or this translucent. This is due to the gold nanoparticles that are embedded within the glass and the interaction between those nanoparticles and the incident light that strikes them. Damascus steel is well known to be very high strong, maintains its edge very well, and part of the reason for that is that all this blacksmith work and hammering and metalworking that was done to create Damascus steel actually created nanoscale crystals of metal that are responsible in part for the strength of the steel. So there were nanotechnologists well before it was a glint in President Clinton's eye or others. But nanotechnology is really around us all today. So not only the cell phone that's in your pocket, but high-strength composites made with carbon nanotubes and, oops, rats. And it's in space, too. Are used in bicycles. Nanocomposites are used to reduce gas permeation and make your tennis balls live longer. Golf balls, I buy a bunch of those because I lose them in the woods all the time. But the clays and other nanoparticles are added to the resin to make it more lively, and so you can get better distance out of it. Again, high-strength composites are used in things like helmets for hockey. Nano additives are used now in coating of fabrics to make them stain and water repellent, and also to make them antimicrobial. So silver particles now are coated onto various synthetic fibers and used to make athletic wear that then reduce the amount of odor because they kill bacteria. In fact, the silver nanoparticles have been used in things such as Band-Aids and as the coating in washers and dryers to, again, deal with killing microbes in there. And then if you wear cosmetics or suntan lotion, sunscreen, nanoscale titanium dioxide is actually used in a lot of those applications, and it turns out that the amount of dermal absorption of the titanium dioxide through your skin is less than more conventional sunscreen-based, organic sunscreen-based, light harvesting materials. So. Nanos, I have to talk about space, right, being from NASA. So nanotechnology has found its way into space in a variety of different applications. Carbon nanotube composites are used on the Juno spacecraft for charge dissipation. So in space, as the spacecraft moves through the environment, there's a lot of ions there. It builds up charge, and that charge can have a negative effect on the electronics within the spacecraft and its ability to communicate with Earth. And so what they did was to take those nanocomposites made with sheets of nanotubes that Nanocomp produced and included those within the rest of the vehicle. My colleagues at NASA Ames Research Center developed a carbon nanotube-based electronic nose that was able to detect trace amounts of certain gases. They did it first for nitrous oxide, and they demonstrated it first on a satellite, and then they miniaturized that sensor even further and flew it on the International Space Station and did several months of experiments that were all successful. They've done a further miniaturization of that and incorporated it as a plug-in unit into a smartphone. And they've worked with the Los Angeles Fire Department to demonstrate that you could use that as a handheld sensor for firefighters to go into a fire and detect where the toxic gases are. And then they could network all of the cell phones together to establish a perimeter around the fire where it was safe to walk. Silica aerogels, we'll talk a little bit about aerogels later, but these are really pretty neat materials. Very good thermal insulators, but extremely fragile. However, these aerogels, silica aerogels, have been used in every Mars rover that we've launched, that NASA has launched as the thermal insulation for the batteries, and you want to keep the batteries warm so that they continue to operate, and these have proven to be quite effective at that. The slide or picture on the right shows the use of silica aerogels in something called the Stardust mission. And the idea of this Stardust mission was to capture particles from the tail of a comet and take them back to Earth so that we could understand, first of all, the chemical composition of those particles, but also the morphology, the shape of the particles. And what's neat about the aerogels as a capture medium is that these guys would get stopped in the aerogel, but they wouldn't get distorted. So you can think about these things hitting something at a very high speed. It's probably likely that they get flattened out and smashed, while the aerogels were able to trap those particles without doing damage. This is some more recent work in polyimide aerogels, which are plastic or high-performance polymer aerogels. This is actually some work that my wife has done, and we'll talk a little bit about that later. But this is a flight experiment out of the University of Puerto Rico in a program called ROCSAT. And ROCSAT is an opportunity for students to write proposals to NASA, and if they're about things that they might do on a sounding rocket payload. And if they're selected, then they get a space on a multi-experiment payload. And the students at Puerto Rico are quite good at this. They're actually sort of ROCSAT machines in which they've written a number of successful proposals. This one was to take and trap particles in the Earth's upper atmosphere and measure the energy of those particles, the impact energy of those particles. So nano is actually used twice here. It's used in the polyimide aerogels to capture the particles, and these silver sort of discs here are strain sensors which are coated with nanodiamond to protect them from oxidation. And then this is actually a frame that we grabbed from the video that they took, and you can see this thing protruding. Here's the payload bay of the satellite. Here's the Earth's horizon here, and you can see this experimental payload, this block here, sticking out of the payload. Okay, so what's so special about nanotechnology? I mentioned to you that once you get small, really small, 100 nanometers or so, cool things start to happen. And those cool things happen and change the properties, whether they're mechanical or optical or electrical or thermal properties of materials. And those changes can be influenced by a variety of different things: surface area, size, porosity, surface roughness, and then a phenomenon called multifunctionality. And what I'd like to do is tell you what happens in each of those categories when you get down to the nanoscale. So surface area is kind of cool. When you get to very large surface areas, and you can get to extremely large surface areas in these nanoparticles, what happens is that the reactivity of the material can change. So what I've got here are two videos. In the first video, I've got a pile of aluminum powder, not nanoscale aluminum, and we're going to touch a match to it and watch what happens. Maybe we'll touch a match to it if I can do this right. Okay. So it burns, and it burns just simply by oxidation of the surface of the aluminum. Now, the second video on the left, or on the right, or your left, oh, you're right. The second video shows what happens if you take a pile of nanoscale aluminum powder and touch a match to it. Okay, get the point? All right, now, again, back to the NASA stuff. So, a very clever experiment that was done by a group at Purdue and Penn State universities involved taking nanoscale aluminum particles and mixing them in water and freezing them. And this nanoscale aluminum ice composite that they called ALICE could be used to make a propellant for a rocket. And this video is going to show you, first of all, just a test stand on Earth that they've done with this propellant, and you can see how effective it is. And then at the end, you'll see an actual rocket that's being launched with it. So what you're seeing here is just on the test stand, they're just doing some demonstration experiments. Pretty dramatic stuff. Now watch this. This is not my video. They got a little carried away. but it's. I mean, that shows you in two examples of, first of all, what this high surface area does for you, and then secondly, how you might use it. That was a small rocket, well, relatively small rocket. You saw a picture of the students in this team holding the rocket, and actually this fellow here is Steve Son, who was the professor at Purdue that was involved in the work, and I don't see his colleague Rich Yetter from Penn State in there, but you can see his students, and pretty exciting stuff. That rocket got to about 1,800 meters in height, and there's been more work done in smart propellants based on these nanoparticles. I guess I don't need to go back there anymore. Okay, what about size? Here's another cool thing. So when you get down to really small sizes, you get novel physics, and a good example is called quantum confinement, where now you're actually getting down to a size that you're interacting with an individual wavelength of light, and you can get some pretty interesting optical properties. So this is an example of that. These are quantum dots. So quantum dots are nanoscale beads of semiconductors. But they can also be other materials, but they're nanoscale beads of materials. The only thing is that these beads have to interact with light and do something. In this case, these beads fluoresce. So what you see on the left here is just an example of how, as I go from very small dots to very large dots, and you're talking about, what is this? 8 nanometers, I can't see this, 8 nanometers in size versus about 1 nanometer. You're seeing a shift from the blue to the red, so to longer wavelengths. And here's just another example of that. So this is the small dots, these are the large dots. And here's just an example of an electron microscope image, a transmission electron microscope image that shows one of these dots and the individual atoms within the dots. There are a lot of applications that you can think about for using these, but a couple of them are actually a commercial reality. The first one is solid-state lighting, and the second is displays. I don't know why I keep going over here, but I am. So solid-state lighting, you're talking about light-emitting diodes or organic light-emitting diodes. The market for this solid-state lighting is projected to be something on the order of $22 billion US by 2020. And I don't know how much solid-state lighting is used here, but in the United States, there's been a move away, actually a mandated move away from incandescent lighting to compact fluorescent or solid-state lighting, because there's a recognition that incandescent lights are very energy efficient. The problem is that we've grown up, all of us, with incandescent lights with this pleasing, warm, white light. And when the first incarnations of solid-state lighting, in particular, well, both this compact fluorescent and the LED-based lights, it was a real harsh blue. And there was a lot of work done to go to a pleasing white. And the way that this is done is you can do two things. You can use an array of a bunch of light-emitting diodes that emit colors that blend out to make a nice warm white, or you can use quantum dots to do that. And here's an example of actually quantum dots are used in all of these systems here. This is just a very thin LED light. So you can think about this in putting in lighting panels in your ceiling or in your wall. I was actually, we were lucky enough to do a couple of side visits yesterday. One was at University of Manchester at their Graphene Institute, and they're using graphene in conjunction with solid-state lighting to make light panels. And then we also had the privilege of visiting with Terry Wilkins and his colleagues later in the day at Leeds to talk about environmental health and safety and other and hip replacements and other things that you can do. Yeah, spintronics. But so here's some examples of just solid-state lighting that's enabled by the use of these quantum dots. And more recently, there's been a lot of work in sort of the holy grail, that is to make a single quantum dot that glows white. And it turns out that this group at Vanderbilt, as well as others, has been successful in being able to do that. And I'm doing it again. Okay, this is cool. I want one of these. My wife won't let me buy one. But we keep going to I don't know if you have Best Buy here, but that's a big electronics store in the States. And they have them right in the middle of the store. And it's like, I need one of these. So again, quantum dots are used here. A company called QD Vision has worked on quantum dots made out of a material called cadmium selenide, and they've developed it into a technology that they call Color IQ. Color IQ was incorporated by Sony into their Bravia TVs in 2013, and I think it's also being now used by Philips and maybe another company, but that I'm not sure. But that TV received the Best of 2013 Consumer Electronics Show, which is a big show in the United States. Their Tech Radar magazine gave them that award. Reduces power consumption by 20%, so it's less polluting. Now, what's kind of cool about this, well, the other thing is that QD Vision, the United States Environmental Protection Agency, has what they call a Green Chemistry Challenge Award, and they give it to companies that do things to replace more toxic materials in their processes with more environmentally benign ones. And so QD Vision was able to replace some phosphorus-containing materials that were potentially toxic with new technology, which is not toxic. But what's neat about this is you could say, well, geez, you're making these quantum dots out of cadmium, and cadmium is really bad. And so really, aren't you making these nanoparticles that are bad for the environment and actually having a negative impact on the environment? But these TVs burn 20% less power, and a typical coal power plant produces cadmium as one of the byproducts of the combustion processes. It's in the coal. And it turns out that you actually reduce the amount of cadmium that's released by burning coal and fossil fuel plants by much more than the amount of cadmium that you put in one of these TVs. And they only put maybe a couple of grams of cadmium selenide quantum dots in these things. But I'm hoping to get one of these under my Christmas tree. Porosity, so that's another thing. So when you get down to pore sizes which are on the nanometer scale, or so, less than 100 nanometers, what happens is now you can restrict the flow of gas molecules through that material. And what that means is now you can make materials which are really great thermal insulators, and also because they're very lightweight and nanoporous, they can be great electrical insulators. So I talked about aerogels, and what are aerogels? Well, aerogels are basically taking a material, producing a gel like Jell-O, and then taking the liquid that's used as the reaction medium to make that gel and replacing it with something, typically a fluid like liquid carbon dioxide, which is at a supercritical point. And when you take that CO2 from being a liquid to a gas, you do it in such a way that you don't collapse the material, and you preserve this structure, this nanostructure that you get in the gel, so you don't distort that nanostructure. So what happens there now is that these things are so small that gas molecules can't move through them very, very readily. And they're great insulators, 2 to 4 times better than fiberglass, just by putting them in your house, and about 10 to 15 times better than fiberglass if you put them under a light vacuum. And I showed some examples of that. This is what an aerogel looks like under an electron microscope. But the market for advanced insulation globally is pretty significant. It's expected to grow. This is a study by Lux Research, again, in the United States, from about $894 million US dollars in 2015 to almost $2 billion in 2019. And these are some examples of commercial products already. So Cabot makes some aerogels that can be used in this translucent lighting panels that are used in the roofs of buildings. Aspen Aerogels makes an aerogel blanket material like this material shown here that they can use for insulating pipes for oil and gas refineries and applications like that. This is an example of how great an insulator aerogels are. So here's a thermographic image of a conventional house with just fiberglass insulation in it, and you can see all the heat leakage that occurs. The green is the green and blue colors are cooler than the yellow and red colors. You can see all the energy that's lost through the windows, but also through the studs. If you take those studs and you coat them with this aerogel blanket material, now you can see that you've taken the heat loss from that building down significantly. And so I know that there's a lot of activity here in the UK and in the EU in making smart buildings and reducing energy, and there certainly is the same interest in the United States in doing that. This is a way of doing that. The issue, and there are a lot of applications in space for aerogels, all the way from tanks for the cryogenic propellants that are used to power certain spacecraft, to the spacesuits that astronauts wear, to this interesting application here called an inflatable aerodynamic decelerator. So say that 3 times fast. What that is a large sort of inverted parachute that's deployed as a spacecraft starts to enter a planet's environment, and it creates drag on the spacecraft, and it slows it down as it enters the atmosphere. Typically, these decelerators are hard materials like the heat shield on the back of the space capsule here. But when we talk about putting something on, for instance, on the surface of Mars, what we would like to be able to do is put very large payloads, and maybe even humans on Mars. And now you're talking about diameters that are on the order of 40 meters or so, and it's just physically too large to be practical in terms of having a hard aerogel to do that. So these inflatable structures are receiving a lot of attention. And in fact, aerogels have been used as the insulation in the inner part of this decelerator to cool it down, to protect it from the heat of reentry. But they're really not that good at it because they're fragile and they tend to decompose under mechanical load. So an example of that is shown here on the left. Here's a conventional silica aerogel, and you can actually take this, and with just pressing lightly with your finger, you can crack that guy, and it doesn't take too much to just crush it in your hand. Great insulators, but not great insulators that you can pack up and beat to death and stuff in a small can before you're going to and then leave it there for months and then expect to launch it and everything will be fine. So some research that was done at NASA was to try to develop alternatives to that, and it led to these new materials called polymer aerogels, or one could say plastic aerogels. And these materials are pretty cool. They, in a thin film form, you can actually fold them up like you need to do for this inflatable decelerator. They're extremely high strength. So this is a smart car with the piece of aerogel block underneath, and you see that the aerogel is not crushed at all by that. You can see the tire, if you take the car off and look at it, you can see the tire track imprint. But neat stuff, and this is not me, this is the other MA Meador in the audience, but basically we've licensed this technology to industry, and are hopeful that it will find its way into commercial products. So you owed me $20, I think, to talk about your technology. Last thing I'm going to talk about is surface roughness. And surface roughness is very interesting because once you get to patterning things, structures on the nanoscale, you can start to control the way that surface interacts with water or with other liquids. And you can get to situations where basically you can mimic biology. So here's an example of a lotus leaf here with some dirt on it or sand on it and a droplet of water, and you can see that now you can make self-cleaning surfaces. And the way that this works is this image here shows these nanoscale pillars, and the pillars are spaced in such a way that the droplet of water actually, that there's some air pockets trapped within the pillars, and the droplet of water actually, or liquid, rides on that air that's trapped there, so it doesn't sink in. This is a screen shot from a video by a company in the US, and I forget the name of the company, but you see these guys, they're standing there with nice clean shirts and pants on that have been coated with this product that's water repellent, and they're probably their colleague gets to have the great fun of throwing a bucket of mud at them and to demonstrate that the mud just slides off, and it does. It's pretty neat. So where can we use these besides making clothing that you can throw mud at and you're fine? Ice accretion. So ice formation is a major problem for both wind turbines and aircraft. For aircraft in the US alone, 25 million gallons of de-icing fluids are used annually at US airports, and it takes a long time to de-ice an airplane. For wind turbines, this makes me chilly just looking at it, but both of these pictures. But wind turbines, the efficiency of the wind turbines is reduced significantly because the aerodynamics has changed when ice builds up on these. And in fact, what they do oftentimes is just shut these down because they don't work well. Plus, they get out of balance, and so now you start to damage the internal rotating machinery of the wind turbine. So here's an example of some work from the General Electric Corporation in which they've put a nanoscale textured coating onto the surface of a structure, and they were trying to do it for both aircraft and wind applications. And what you see here is just how long it takes for the ice crystals to start to form onto the surface of the substrate. So this is without that magic coating, and it forms within just a few seconds. But now you can delay the formation of that ice by several orders of magnitude time by putting that nanoscale coating on there. You can also think about nanoscale or nanotextured surfaces as a way of doing things like inhibiting the growth of bacteria. And as you know, disease and infection due to microbial resistant bacteria, antimicrobial resistant bacteria, is a big problem worldwide. In the US, I think there's something on the order of $40 billion a year is spent in dealing with infections that result from that, and it can be pretty nasty and life-threatening. So here's an example, and drugs, and bacteria are getting smart. They figured out a way to get around different drugs. They've even figured out a way to get around certain nanoparticles, which is kind of scary. But they have not figured out a way to do this. So you can actually make nanotextured surfaces that can do a variety of different things. First of all, they can inhibit the formation of the biofilms that cause the bacteria to stick onto surfaces. And the second thing that they can do is they can actually kill the bacteria by, if they're sharp pointers, they sort of jab the bacteria and kill it. And I talked to an expert in this area last week at a brief meeting that I was at, and she felt that this might be a way to actually, finally have the last word on antimicrobial resistant bacteria, because they don't think that this is potentially is not a way that bacteria can figure out how to get around. Multifunctionality, I don't have a slide on this, but the basic idea, I actually did have a slide, and it's the aerogels. So multifunctional materials, and I'll give you a nice example of this, are structural materials that do something else. So they're part of a spacecraft or an aircraft, and they do something else. The one that I always talk about is radiation protection. So I don't know how many of you saw The Martian, great movie. But for a long-duration mission to Mars, we have to develop technologies that are lightweight that will allow us to protect the astronauts from just the ambient radiation that's around them all day. So it's just low-level chronic exposure to radiation. The typical things that are used for that are things like water walls. So water is extremely heavy, and if you're going to go to Mars and hope to come back, you really have to think about ways to do that in which you minimize the weight of the spacecraft itself. And so the water walls they're very effective, but they're very heavy. So can you think about making a new material that is inherently good at shielding against radiation, but also has enough mechanical properties that it can be made part of the vehicle itself? And there are ways that nanotechnology can do that. Carbon nanotubes, boron nitride nanotubes are a couple of examples. The one example I showed here was the aerogels, because now they're great thermal insulators, but they also have good mechanical properties. So you could think about making, for instance, a cryogenic propellant tank that had the insulation on the outside of the tank is actually part of the actual structure of the tank itself and providing structural integrity for it. Okay, so what's nanotechnology going to do in the future? How am I doing? Oh my goodness. All right. I did put too many slides in. So let's talk about treatment of disease. This is some examples of current things that are going on right now. Nanotechnology allows you to do targeted delivery and treatment of certain diseases, whether it's these nanoparticle drugs such as the Bind nanoparticle that's actually gone through phase 1 clinical trials in the United States, whether it's these nanoemulsions that have been demonstrated for the treatment of infectious diseases like hepatitis or dengue fever or even Ebola, or whether it's making nanoparticle drugs for cancer immunotherapy that actually trigger certain aspects of the body's immune system that it can go off on its own and fight cancer without having to rely upon these drugs. Nanotechnology has also been used in medical diagnostics. There's 3 examples here. The first is an electronic nose, sort of like the nose that I showed you earlier, that basically is tuned to detect volatile biomarkers for certain types of cancer. So it turns out that if you are unfortunate enough to have certain types of cancer, that your body will emit through your breath or other means small molecules like alcohols or certain things, certain types of alcohols, that you can then tune these sensors to detect, and you can do it just by breathing into these guys and be able to detect them. This is neat. These are actually tattoos that are made out of nano-patterned electrodes, and the idea with this one is that you can actually measure the effect of mechanical properties of loading on the skin. Now, you may not want to, it's more to do biological studies on this, but you can think about, making other types of non-invasive sensors using this sort of an approach that you could do to maybe measure, your heart rate or oxygen rate, or even whether you have if you have diabetes, what your sugar level is. I have a device on my wrist called a Fitbit, which probably a lot of you have, that records the amount of steps that I have, and it records my heart rate and tells me that I didn't sleep enough last night, and things like that. But you can think about making wearable, flexible electronics that allow you to do the same thing. And the United States government is under the Advanced Manufacturing Program, will be announcing later this year an innovative manufacturing institute focused on flexible electronics that will look at doing things just like this. The last one is a nano-silver-based colorimetric sensor for the rapid detection of Ebola. So this, by tuning the characteristics of the silver nanoparticles and then embedding them on sort of these paper sensors here, you can get a way of detecting Ebola rapidly on the order of 15 minutes or so, rather than taking several hours or days to do it in a clinical laboratory, and you can do it fairly reliably. So it's sort of like a test that you have, the equivalent of a pregnancy test, but in this case for Ebola. What about food packaging? Well, again, that's a big problem. I don't know how it is in the UK, but in the US, about 40% of all food grown in the United States is never eaten. It just simply spoils, it's wasted. And the issues are, how can you reduce spoilage in the food by developing better packaging, but also can you make smart packaging that has sensors embedded in it? So you look at it and you go, well, the the throw it away date is today, but the sensor says I'm still good. I don't have to throw it away. Here's an example of how nanotechnology can reduce spoilage. So we can think about doing things like adding clay to the plastic film that's used in the packaging. And when you do that, you create a structure that looks like this on the left, in which you've got, these are individual platelets of clay, and they organize in the film like this. And so you create a situation where oxygen has to travel a much longer distance to get through the film to induce spoilage than just in the straight film itself without those clay particles in there. And so you can really reduce the permeability of that film to oxygen, and in doing that, reduce spoilage. But I want to show you two examples. First is packaging, and the second is sensors. This is active packaging. So what they've done is to do two things. They've used the clay to do exactly what I talked about on the prior slide, but then they've also included a natural oil called carvacrol, which is a phenol-based compound, which is an antioxidant. And what it does then is it also reduces the oxidation and spoilage in the packaging. And so you see here that they're reducing the amount of, this is just with the essential oil in there, but now when you add clay in it, that you're actually reducing the amount of bacteria by 8 or 10 orders of powers of 10 rather, and so the effect is pretty remarkable. This is smart packaging. So now this is a detection system, just a dot of a dye that changes color when it's exposed to oxygen, and by itself, the dye is colorless. And so what you do is you add a little bit of titanium dioxide in there. It changes the color of the blue dye, which is what color it turns to when it's exposed to oxygen. Takes it back to its original form, colorless. So here you've got the meat that's packaged in this thing just after you've sealed it up, and because it's been in contact with the air, it's blue. Now you shine light on this guy, and you bleach the dye out, but it's still able to turn blue. Now you've just cracked this open a little bit, and you can start to see the blue sensor. Actually, this is on the outside, I'm sorry. This is on the outside of this, so just exposed to the air outside, it turns blue, as it ought to, because the oxygen is there. And now you've breached the package, and you can see that the internal dot turns blue as well. So you can think about using this. This is just one example, but there are other countless examples of being able to do that. And then the last is about sensors for the detection of foodborne pathogens. And basically the idea here is that you can use nanoscale particles and put certain groups or compounds onto the surface of these that will interact with bacteria. And when they do that, they change the properties, the optical or the electrical properties of the nanoparticles change. And you can even make these into handheld sensors like the one shown in this picture above. This is kind of neat. This is generating nanoscale particles of water to basically wash and disinfect fruit and vegetables. And what they do is they have a tip with a very high electrical charge on it, and they put just a drop of water on there. Charge builds up in the water droplet, and it breaks up into small particles of water on the nanoscale. And it's much more efficient in terms of its effect to wash away bacteria. The other thing that happens is that the electrical charge actually decomposes the water and makes free radicals, which actually then go ahead and kill the bacteria. So it's sort of like you've washed it off, but then you've killed it, sort of the second measure. Desalination is another big problem. In the United States and in California right now, they're having Southern California, they're having a crisis with water, and they're actually restricting the amount of water usage. If you could just take and develop a cost-effective way of desalinating water and make it affordable for everybody, you could impact California, but other places around the world. This is an example of actually drilling nanoscale holes into graphene and using that as a way of filtering out things like sodium chloride. And it's quite effective at doing that. And one of the issues with these nanoporous membranes is that they're great at taking out ions or bacteria or organics, but the water flow, the flux through these things tends to be quite low because they're nanoporous, just like the flow of gases through that aerogel is restricted. And so this is a way of actually getting flux rates up. And in the US, Lockheed Martin has taken this and developed a class of materials called perforines, which are perforated graphene, that's about 100 times better than typical, has better flow through the membrane, these perforating membranes, than reverse osmosis membranes that are used right now for water purification and desalination. Okay, this is the last couple of slides about nanotechnology in the future, but this is, can we develop these exquisitely ordered structures called hierarchical structures that mimic nature? And nature does this quite readily, and they do it for a variety of different reasons. So, for instance, the gecko, the feet of the gecko lizard, has all these nanoscale hairs called cilia, and these guys will actually allow that gecko to crawl up the wall. And the reason that happens is that you have attractive forces, electrostatic forces at the tip of the cilia that interact with the surface and are strong enough, all of them together are strong enough so that the gecko can't slide down the wall, but if you pull him this way, he comes off. You can think about using that maybe to make adhesives that are really great in one direction, and you can actually reuse them by yanking on them. The shark grows these textured scales onto, textured surfaces onto its skin, and in doing so, it allows it to reduce aerodynamic drag so it can swim through the water much faster. You saw the lotus leaf, self-cleaning structure, and then even bone, human bone has this nanoporous structure that actually has a very ordered structure that allows oxygen to get through the bone to keep it healthy, blood to flow through the bone, and also minimize mass and be structurally efficient. So can we use nanotechnology to do the same thing? And in fact, we can. This is some work on the left out of Caltech and the Hughes Research Lab, in which they have developed these nanolattice structures out of metals, and you can see that they're extremely light. This is the dandelion flower, and this picture has led to a whole rash of other lightweight structures in the same stupid photo, but it's, it shows that these are extremely lightweight. So what's neat about this is here's an example of more work out of Professor Greer's lab at Caltech. These nanostructures have properties which are mechanical properties which are significantly different from the bulk material that they're made from. So for instance, in this picture on the right here, they've designed these pretty complex structures, even more complex than this, and they've built them out of a ceramic, and the ceramic is very brittle. But what you find when you design these things properly is that these nanolattice structures are actually elastomeric, and you can squeeze them, compress them quite a bit before they fail. So you can think about, can I put things together, and in doing so, get into these nanoscale structures, these nanolattices, and get properties which are radically different from the bulk material that they're made from. This is another example of using actually 3D printing to make graphene aerogels that are then used as multifunctional materials in a fuel cell electrode. But what I find particularly intriguing about this is that this is all done with really larger nanoscale and even microscale constituents. And you can see that even in that case, you go from a material which has one property in the bulk to another property when you get to this different type of architecture. And it's sort of similar to what happens in nanotechnology. That is, I can take a bulk piece of cadmium selenide, and it only has a certain optical spectrum. But if I change the properties to the nanoscale, as we did with the quantum dots, I can change the light that comes out of that cadmium selenide to just about any color in the spectrum that I want. So could you take nanoscale additives and assemble them in a hierarchical structure so that now you have something which is even more different than what you've had before, and now you're opening up a whole new design space and things that you might be able to do. So I think that stay tuned, but I think that's one thing where nanotechnology is headed. I just wanted to talk a little bit about environmental health and safety, and then I'm going to, and a little bit about actually how the United States and the UK and the EU are collaborating, and then I'll finish up. So environmental health and safety is a big thing because being able to understand and control the risks associated with exposure of the humans and in the environment and animals in the environment to nanomaterials is important. It's important because we really need to be responsible about this and protect workers and consumers and the public and the environment both today but also in the future. So I make this great product out of a nanomaterial, and I'm done with it, and I throw it out, and it goes into a landfill, what happens, 20 years down the road? We want to make sure that that's safe. The other thing that we want to do is in regulating these materials, we don't want to come up with regulations that are unnecessarily restrictive to the point where there's no way that we'll ever make that product out of that nanomaterial. So you want to be responsible in how you regulate nanotechnology, but you want to do it in a science-based method so that you know at the end of the day that what you make is safe, but you've regulated it so that you're not making it impossible to commercialize it. But it's a tough business to do this. Environmental health risks associated with nanomaterials really are a function of two things: the toxicology of the material and the risk of exposure. And so there's work going on in both areas. In terms of, but being able to do this is difficult because the characterization of the toxicology behavior of engineered materials is confounded by the fact that around us there are naturally occurring nanomaterials. And so it's sort of like, how can you identify the nanomaterial in all the other junk that's around it? If you are in a shop where there's a lot of welding that goes on, for instance, there are tons of carbon and metal nanoparticles around. Your automobile puts out nanoparticles out of its exhaust. So there's stuff that goes on all the time, and nature does it, but just by the natural mechanical or other forms of degradation of the material. So when you think about having to find this nanomaterial, a person at this meeting that I was at last week said, it's like trying to find a needle in a haystack, and the needle's made out of wood. So you have to be clever, and the science that's needed to develop the characterization techniques that are selective enough to find the needle that you're looking for is important. The other thing is that a lot of times people take these toxicological studies to the extreme. So the trend, the inclination of a scientist is to say, well, if I do this and this effect happens, what if I do this more? And what if I do this more? And so, and I'm a chemist, so I can make fun of scientists that way. And I've done those studies, not on toxicology. But the issue becomes that at some point, if you just keep adding nanomaterials, yeah, you're going to kill whatever you're adding it to. You might not kill it because of the nanomaterials you've added, but you've suspended the nanomaterials in water, and now you're drowning the poor mouse that you're trying to test them on. So the conditions are sort of specious. So that's not to say that these are all bad studies. There are a lot of great studies, so please don't misunderstand me. But these are some of the realities. So a lot of work has been done not much work though has been done to understand exposure, and there's a lot of work going on now within the United States under the auspices of the NNI, looking at really trying to understand what do we know, both in terms of exposure routes and how different nanomaterials get into your body or into plants or into the environment, and then also the toxicological studies. So is it really, is it bad for you? Because if risk is a function of both how bad the material is and how likely it is to get in your body, then if the material is not toxic at all, you don't care. If there's no chance in a million that the stuff is going to get into your body and do damage, then maybe you don't need to worry about it. So that's the whole idea behind making this informed decisions about risk. So we just recently had a workshop with the U.S. Consumer Product Safety Commission in July of this year to talk about this issue, and a report will be coming out on it soon. And I'm going to skip through this because I know I've been going on forever. But just basically to say that because the NNI knows that EH&S is a big problem, and because of the work that was done here, actually, we've developed a strategy for funding EH&S and directing future EH&S research activities in the United States. We released a plan for doing that in 2011. We updated that with a progress review in 2014. And also, this is a great opportunity to collaborate, and this is probably the single best area where there has been collaboration and a lot of opportunity for future collaboration between the United States and the United Kingdom and also the European Union. You can see a variety of different activities. OECD is doing quite a bit of work in this area, but also standards, not only standards to make sure that everybody's on the same page when they do these toxicological assessments in terms of protocols and also just definitions of what a nanomaterial is and stuff like that. But then also doing things like collaborations under activities like the Communities of Research and the EU. That's a collaboration with the US. The other thing is that I think that nanotechnology is a great opportunity to inspire students and to get them to think about science and technology, engineering and mathematics. You know, here's a few examples of this. In the right, a young student from high school who was an intern at the NASA Ames Research Center worked on a nano-based sensor, and she actually got to go to the White House Science Fair and talk to President Obama, Professor Obama. Maybe he was a professor at one point, a law professor. There's an activity in the United States that was funded by the National Science Foundation called the NISNet, which was basically designed to do public outreach, and it was led by the Boston Museum of Science. And they did a whole variety of different things. One of them was to actually develop an annual Nano Days activity, and they developed a set of kits and instructional material that could be used by museums throughout the United States and other institutions to educate students and the public about nanotechnology, and they reached millions of people over the course of their grant. This bill up here, this announcement, is actually from the University of Puerto Rico in Rio Piedras, and I had the opportunity over my career to work with the folks there, and it's amazing how hungry people are in Puerto Rico for information about science. They can have an event where it's just looking at the stars, you know, an astronomy night, and they can draw 10,000 people to this thing, you know. And I think about what goes on in the United States, and you set up, you know, they just set up a couple of, like half a dozen telescopes, and they get all these people to come. If I think about my home back in Cleveland, you put up those telescopes, you maybe get 100 people. You know, I mean, it's sad, but it's true. But can we think about ways of doing that? Can nanotechnology be a platform for really being sort of like the next Apollo? You know, for those of us that grew up in the 60s and saw the whole Apollo missions and that made us want to go into careers in the field. I think that there are opportunities within nanotechnology to do that, and some of the things that have gone on in the U.S. but elsewhere are great examples of how to do that. Just a shameless advertisement. If you want to find out more about what's going on in the National Nanotechnology Initiative in the United States, there's a great website called Nano.gov. And you can find out a lot of things that go on, including an announcement that was made today about a grand challenge in nanotechnology. So the NNI gets reviewed every 2 years by the President's Council of Advisors for Science and Technology. And they did their last review last year. And in their review, they said that the NNI ought to consider using grand challenges as a way of managing part of the research within the NNI and building a stronger sense of community, exciting more and more people about the possibility of nanotechnology. And these grand challenges are really very bold, audacious goals. So, you know, could be developing access to clean drinking water for everyone, regardless of where they live. And then, but things that you can do in a 10 to 20 year horizon. And things that in this case, things that nanotechnology could do. Now you could say, well, you know, water treatment, I can do that, and it doesn't have to be a nanotechnology solution, but nanotechnology could be an important part of that solution. And so what happens with PCAST is that they meet every 2 months, and every other meeting they get FaceTime with the president. So 6 months ago, they met with President Obama, and they decided to tell him about their review of the NNI, and they got to grand challenges, and the president said, oh, that's a great idea. So the memos are flying all over the government. We need to do grand challenges. You will do grand challenges. So we did we did some internal planning within the National Nanotechnology Initiative, where we had a one-day retreat of all representatives from all the individual agencies within the NNI, both those that fund research and those that don't, we developed some potential lists of grand challenges that we thought would be appropriate. But then what we did, we went one step beyond that, and we actually put out a request for information to the public. And we said, okay, here are some grand challenges that we think are not bad ideas, but these are not by any means, you know, the final list. We ask you to do three things, one of three things or all three things for us. Look at these grand challenges. If you think they're great, tell us how you think how you would approach them. If you think they're sort of great, but they would be a little bit better if we changed this, you know, this objective, then please tell us that. And if you think we're all wet and you've got a better idea, tell us that. And we had this RFI open for about a month, and we received over 100 responses. Some of them said we were brilliant, and some of them said we weren't so brilliant. And so as of today, this morning in the United States, ta-da, we announced the first nanotechnology grand challenge. And it is to create a new type of a computer that can proactively interpret and learn from data, solve unfamiliar problems using what it has learned, and operate with the energy efficiency of the human brain. Basically, the idea here is by using nanotechnology in conjunction with other technologies, can we make computing systems that move beyond the typical von Neumann-based computing architectures that we've used forever? And in doing so, can we make computing systems that are capable of solving much larger problems than today's computers can do or could ever possibly do, and doing it using much less energy. So for instance, the brain uses 20 watts, roughly 20 watts of energy to do all its thinking. A light bulb. You know, you're talking about tens of, you know, hundreds or kilowatts for the highest computing systems. So significant reduction in the energy that's required to do that, power that's required to do that. And then the other thing is that your brain can do things that computers just can't simply do. A great example is pattern recognition. You know, you can see an image of that. I can see that and say, okay, you tell me that's a newspaper. The next time I see it, I know it's a newspaper. I don't have to be trained anymore to do that. But with a computer-based vision system, you have to do extensive training to be able to do that. So this was announced today. We expect what will happen is that already there have been some funding commitments announced from certain federal agencies, and also with private foundations and groups like the Semiconductor Research Corporation. There'll be a lot of activity that will go on in terms of saying, okay, here's the challenge, but how are we going to do this, and what might we ought to fund? And my suspicion is that there will be additional dollars that will be put in the next budget, the 2017 budget, to continue to do that. So, at any rate, I hope what I've told you today is that nanotechnology is real, but also that it's at a crossroads. So there have been significant investments made in nanotechnology, and they also continue to be made in the U.S. alone, $1.5 billion US. That's pretty big money. And research, development, and commercialization that I've shown you, I hope, some pretty remarkable advances that have been made, and some things that are in the laboratory or early stages that show a lot of promise. The cancer therapeutic that I showed you passed phase 1 trial in the U.S. There are about 17 drugs, nano-based drugs, that are in various stages of clinical trials within the U.S. alone, and several in the EU. So what's next? Really, to continue to make breakthrough advances, you have to think about doing things that are a little bit outside of the box. One of the topics now that's being talked about is convergence. So convergence means, can I take nanotechnology, biotechnology, information technology, cognitive science, and use all those tools that are available to me through those, you can tell I've talked too much, through those different types of disciplines, and solve new problems in ways that are not possible by just looking at a nanotechnology-based solution. So we talked about the grand challenge, you know, that maybe nano is one way of solving it, but can I take nanotechnology and information technology and biotechnology and do them all together and make a computer that works better than the brain, or than today's computer, not than the brain. I think that there also needs to be an increased emphasis on nanotechnology-enabled systems. So what that means, my colleague Mike Rocco at NSF, who's also the big proponent of convergence technology, says that we need to get away from making nanotubes into making systems from nanotubes. So we need to get away from making nanotubes to making nanotube yarns, to making nanotube yarn reinforced composites. And we're doing that, but we need to do more of that. And I think you're going to see, at least in the US and I'm sure elsewhere, a transition from that. That doesn't mean that the fundamental science that leads to the next breakthrough is not going to happen and there isn't going to be investment in that, but there needs to be more investment in this other area. And then we also need to make progress on commercialization. So $22 billion over the life of the NNI, lots of commercial products, but we could certainly do better. And we need to think about smart ways in which we can foster commercialization of technology, foster an awareness of what comes out of the laboratory so that businesses can pick that up and do things that remove the impediments to commercializing nanotechnology. And again, our favorite topic is the H&S, right? And how can we really do the science necessary to enable smart regulation of nanotechnology to reduce or eliminate risk. And when you do that, you can think about impacting things like the insurance and liability. We had the chance of visiting today with a bunch of folks from the insurance industry and talk about that. And I thought I understood the problem, but I really didn't. And now I really understand the problem, and it's big. And so I think more work needs to be done in that in other areas. I think we also need to think about increasing efforts to educate students and the public. There's a debate in the United States about, do we have enough of a skilled workforce or don't we? And there are two camps. But what we keep hearing time and time again from, at least in the United States, from businesses that are working in nanotechnology is they don't have access to enough skilled workers. And it's not going to get better, it's only going to get worse. I mean, hopefully as nanotechnology and industry develops more and more and more, that demand is going to go up, and we need to think about better ways of educating students. We also need to do a better job of educating the public about the awareness of the risks and the benefits of nanotechnology. And for us in the United States, we have a duty to do a better job of telling the public, you gave us $22 billion, what did I get for that money? And so, hopefully we're going to try to do more. And then I mentioned this, but really, can you use nanotechnology as a tool to stimulate interest in students in pursuing a career in science, technology, engineering, and math? We do fine with stimulating kids to want to go into being soccer stars or basketball stars or things like that. But can you really make science cool? And maybe nano is a way of doing that. I certainly hope so, and we're going to try to do in my office more things along that area. And then I think that it's really important to develop global partnerships to tackle the hard problems. There's a lot of work to do in this area, in EH&S, in fundamental science, in novel ways to do commercialization, in you name it. And a lot of the problems are extremely hard. We all are in an era of constrained budgets, and we just need to think about smarter ways that we can work together. So, boy, have I gone on for a long time. I'm sorry. I only meant to go an hour, but my wife usually edits my slides. It says, you have enough already. You have 80 slides and you're going to talk in an hour? I think I only had 50. But once again, I want to thank the organizers and the Royal Institution for the chance to do this. It's been a thrill for me, and thank you for coming. And I would be happy to answer any questions. Are we okay? Can we do some?
I think, just firstly, thanks very much. I appreciate it is 8:30, so some of you I know may have trains to catch or places to go. I think just while we are here, though, I think I want to do maybe sort of 3 questions, maybe 1 question from each section, just quickly.
I'm really sorry, I didn't need to go on.
So if you could just raise your hands, we'll try and take 1 question over this side. Anyone raise your hands? No? No questions? Anyone with a question? Oh, question here.
You said that you're the chemist, which I am not, but from what you've described this evening, it looks to me as if you've put the water treatment people completely out of business. Because, as you know, with water, when it gets to things like in a condenser or in a boiler, when it changes temperature, the solids tend to come out of it and coagulate around the pipework.
Right.
So would you say then that nanotechnology could cure this problem altogether.
Yeah, I think because you can get away from doing things like that. I mean, certainly, so you can do things, you know, the coatings, for instance, that I showed you. You could think about treating the inside of a pipe or the treatment system with the coating that would tackle some of that issue. I think that Nano has the ability to do several things related to water. It has the ability to develop more efficient ways of treating water, whether it's salt water or brackish water or things like that. It also has a way of being able to detect things in water, pathogens or toxins. And then the third thing that it has the ability to do is to reduce the amount of energy used in even things like transporting water. So if you can control the wetting of the inside of a pipe, for instance, maybe you could be able to pass that water through the pipe with a lot less energy, and your pump wouldn't have to work as hard. So I think there's a lot of potential there, and there's a lot of activity going on in all three facets of that, and I think progress is going to happen pretty rapidly.
Thank you.
Sure.
Very quickly, we've got a question over there. Thank you.
Well, first of all, thank you for a fascinating
Thanks.
talk. It's obviously a very exciting science you're involved in. And I just wondered, it seemed to me that you have some kind of infrastructure in the US whereby people doing very bright people doing the pure science, studying all the quantum mechanical effects, etc. Then you go to people that look at all the technologies and what's available. It seems to me you need that, and perhaps another area where people get through the environmental issues, health and safety. Do we have anything like that in this country? Do you know, or and if so, do you think it's adequate? I wonder what's happening in this country.
Yeah, I'm less of an expert on what goes on here in the UK, and so I don't feel comfortable in commenting on that. Terry, can I put you on the spot?
I was thinking of a question to ask afterwards.
Okay.
Could you repeat the question, please?
So how is the UK doing in terms of spanning things from fundamental science to
just in terms of the whole infrastructure? You seem to have you've got the NNI and you have various initiatives going on. I just wonder whether they have this sort of pure science bit, it's then part of the technologists that can work out what applications and then how to get it to market, etc.
Yes, I think we can answer that. The science base is very strong because of the responsive mode available for scientists and engineers to really go forward and not have to hang around. But within the UK, we've had a body called the Nanotechnology Strategy Forum, which has been co-chaired by the Minister of Science and Universities and the Minister for Environment in DEFRA. We focused on building up the strength of the knowledge transfer network, which has we detect an awful lot of SME activity, rather more perhaps than from some of the bigger countries, bigger companies. Bigger companies are more active, I think, in mainland Europe. But I'm very encouraged by the SME activity, particularly in the biomedical area. So that is being supported and sponsored by the government through the KTNs. There is the catapult structure, which this guy next to me is very involved with. The catapult is blind to technology. If the technology is good, whether it's nano or whatever, you can get late stage development funding for quite big initiatives for advanced manufacturing. So those are the sorts of areas where it's all happening.
I do appreciate time is getting on, but if there's one final question from the centre, particularly if there's a young person, someone younger than me, that would be great. You look reasonably young.
I was just wondering about whether you could use quantum dots to store memory or not.
I think you can. You could certainly think about encoding information into quantum dots. One example that I did not show was that there was a study done by IBM in which they took an array of individual atoms of iron and used the magnetic response of the iron to encode information, and they could then read it, and actually in the that chart that I showed you, there was a data point for that. It's a pretty effective way of doing it. I think some of the other methods, like the DNA encoding, I think is a very powerful technique in terms of the amount of information that you can store, and that also you can take advantage of sequencing technologies that are, you know, pretty tried and true these days.
Well, I think time is running on a bit, so I'm going to have to wrap it up there. I just want to say another few quick thanks. Thanks again to Harry Bashong here and Alan Galwick from Lockton, who helps bring your speakers to us tonight. So a big thank you to them. Thank you to Marlo as well from Nano.gov. And also, I've just been asked to mention OCL as well, who are also the co-sponsor of this event. So very big thank you to them for bringing a speaker to you tonight. And I don't know how much time you have and how jet-lagged you are, but I don't know if you'll be able to stay around and answer a few questions, because I'm sure there's a few people who might want to come up. So do please do that. Once again, thanks very much for coming, and see you again soon. Take care.